Here we begin with a small graph. In order to search this graph, we need some form of traversal. This first one is depth first traversal, or DFT. We will continue down paths until we can't continue anymore, and then backtrack to the last spot where there is a fork in the path and go down another. The starting vertex does not matter and will usually be provided by the user. For this example, I'm going to start at E. During this traversal, I will use a stack to assist me, and then just mark down what order we visit the items in. So to start out, I will change E from being unexplored to visited, and then add it to the stack and order. The top item of the stack will be the current vertex with which we are concerned. Currently, we are focused on E, so I want to move down an edge that is incident to E. There are 3 for this vertex. It doesn't matter which one you choose. As we travel down the edge, we mark it as discovered. This brings us to vertex C, so we can mark it as visited and add C to the stack. Since C is the top item on the stack, it is now our current vertex. So we repeat the same procedure. We arbitrarily choose one of the unexplored edges incident to this vertex and travel down it, marking the new vertex. Occasionally, there will only be one incident unexplored edge, so it will be our only choice. Here we have an unexplored edge, but it leads to a vertex that has already been visited. We don't want to visit it again, so traveling the edge would result in us simply going back to G. Instead, we mark this edge as a back edge. When a vertex no longer has any incident edges that are unexplored, we remove it from this stack and focus on the new top vertex. Here we go all the way back to C. A dead end is another situation where we will not have any more unexplored edges to traverse. If the graph contains other items, they will not be visited by this traversal. We can use this to determine the connectivity of the graph. Now let's apply this traversal method to solve a maze. Here I have a simple maze. If I add a vertex at each spot in the maze, and then I add edges between these vertices that are not separated by a wall, and then I remove the maze, we're left with a graph. I'm going to use the same method here as before and just speed it up a little bit. Starting at vertex A, our goal is to reach vertex Y. The traversal will continue taking paths until it can no longer go any further. Then it will move backwards to a vertex where it can continue. Eventually, this method would visit every vertex in the graph, so we are guaranteed to find a way to vertex Y. One nice thing is now our stack will contain the path of vertices to get from A to Y.